Indian tectonic plate could be splitting into two. Let me repeat that so that sinks in. The Indian tectonic plate could be splitting into two. I will start with a question. How do you think the Himalayas were formed?
India is on the brink of being torn in two, with massive cracks emerging in regions like Ladakh, Himachal Pradesh, and Uttar Pradesh. These sudden changes are linked to the Indian plate breaking apart under the heavy Tibetan Plateau. Now, this same force is making the plate split into two layers, which could mean a shaky future for the area. Could India split into two continents? And yet this alarming development has barely made headlines. What will happen to the nation? Join us as we investigate beneath the landscape and the implications of this occurrence to the entire nation. India's emerging geological threat. This newfound understanding could transform our current concepts of mountain formation and seismic prediction. The ongoing division and deformation deep beneath the Earth's surface might also influence the future geological stability of the region. Moreover, as the Indian tectonic plate continues to push beneath the Tibetan Plateau, it is effectively splitting in two. This geological breakup has significant implications, potentially redefining our geological maps and challenging our understanding of how the Himalayas were formed. Historically, it was believed that the towering Himalayas resulted solely from the collision of the Indian and Eurasian plates. However, new theories suggest a more complicated narrative involving three tectonic plates, including the lesser-known Ksharoda plate, along with the Tethys Ocean, playing crucial roles in this tectonic interplay. As the Indian plate separated from Gondwana and moved northward, it initially collided with the Eurasian plate about 50 million years ago, a pivotal moment in the formation of the Himalayas. Recent theories and geological models suggest a more complex interaction, possibly involving intermediate collisions with smaller plates or island arcs like the Khoestan-Ladakh arc before the significant India-Eurasia collision. This collision pushed the oceanic parts of the Indian plate down into the mantle, causing the uplift of the continental crust above and forming the Himalayas. This involved intense folding and crumpling of the Earth's crust, driven by significant tectonic forces. Recent seismic data and studies offer a deeper understanding of these processes, showing that the Indian plate may be splitting into layers beneath the Tibetan Plateau. This revelation adds complexity to traditional models of Himalayan formation and suggests ongoing geological activity that might continue reshaping the region's landscape. This evolving narrative not only reshapes our understanding of geological processes, but also introduces debate among scientists. Some argue that the Tethys Ocean was merely a large body of water and not a tectonic plate, and that other smaller plates and microcontinents like the Lhasa block were crucial to the Himalayas formation. Continue with us as we explore the heated discussions surrounding the fate of the Indian plate. The entire Indian nation could split in two. Every few years, startling claims about continental geology emerge, and recently it's the Indian subcontinent's turn to be scrutinized. Not long after Africa experienced dramatic geological changes due to vast ground fissures, sensational headlines are now suggesting that India might split into distinct pieces. Recent findings suggest that regions like Ladakh and Himachal Pradesh might break off the map, a situation that has sparked both concern and a surprising measure of indifference. This notable claim's primary argument focuses on the behavior of the Indian plate, a massive section of Earth's crust. Some theories propose that the Indian plate is undergoing a significant transformation, effectively tearing itself in two beneath the vast Tibetan Plateau. Although the notion of geological self-destruction is captivating, the reality may be less dramatic. Numerous experts endorse the idea that the Indian plate is fragmenting, viewing geological data as a signal of an impending catastrophic event. These supporters frequently use vivid imagery to describe the scenario, suggesting that such a split foretells significant geological changes. They contend that the movements of the Indian plate are not mere ordinary shifts, but signify a deep structural transformation that could have extensive effects on the region's geography. Conversely, critics challenge this apocalyptic view. They argue that the notion of India on the brink of a physical split is an exaggeration, propelled more by a quest for dramatic headlines than by solid scientific evidence. These skeptics believe that while the Indian plate is indeed moving, these shifts are typical of the slow but dynamic nature of tectonic movements observed worldwide. They urge caution against interpreting these movements as signs of an imminent geological disaster. Geologists studying this region utilize various tools and methods to monitor the Indian plate, including satellite measurements, seismic sensors, and geological field studies. Updating seismic zoning maps, reinforcing building codes. By analyzing the movement rate and the forces involved, scientists can develop models of the tectonic activities occurring beneath the Tibetan Plateau. The debate hinges on different interpretations of the same data. Some scientists point to rapid movements and unusual seismic activity patterns as indicators of the plate's fragmentation. They note that the northern part of the Indian plate, in particular, shows signs of intense tectonic stress and strain, potentially signaling a split. In contrast, opponents of the split theory suggest that the data can be interpreted differently. They maintain that the observed seismic activity and plate movements are within the expected range for tectonic processes in such a geologically active area. They highlight that similar patterns are observable in other world regions where plates are not splitting. The region's geological history adds another dimension to the debate. For millions of years, the Indian plate has been advancing northward and colliding with the Eurasian plate, leading to the rise of the Himalayas. This significant mountain range itself serves as evidence of ongoing tectonic activity, but does not necessarily indicate that the plate is splitting. Moreover, the geological community remains divided on how to interpret the long-term implications of these movements. While some anticipate that the stresses will eventually lead to notable geological events, others view these as normal occurrences that will not result in dramatic changes. The concept of a plate splitting is not unprecedented. For example, the African plate is known to be undergoing a similar process in the East African Rift, where it is visibly splitting the African continent and forming a new ocean basin. Supporters of the Indian plate splitting theory often cite the African Rift as an analogy, suggesting a similar process could be underway beneath Tibet. This division within the scientific community does more than stir debate. It underscores the complex and often contentious nature of geodynamic research. The possibility that the ground beneath millions could split taps into deep-seated fears and fascinations, yet the actual mechanisms of such dramatic geological phenomena remain under intense scrutiny. Is the Indian plate genuinely breaking, or are these claims merely a reflection of our affinity for dramatic narratives? Get ready to see how rising seismic activities are reshaping landscapes across northern India and Nepal. The alarming increase of powerful earthquakes in North India. The Indian plate, part of the extensive array of tectonic plates that envelop our planet, is currently undergoing significant changes. As it fractures, it activates fault lines and releases seismic energies that cause the ground across the Indian subcontinent to shake. This dramatic geological activity is leading to more frequent and intense earthquakes throughout northern India and Nepal. From January to November 2023, this region experienced close to 97 earthquakes, ranging in magnitude from 3.0 to 3.9. Additionally, there were 21 recorded earthquakes between magnitudes 4.0 and 4.9, highlighting a trend towards more frequent and powerful seismic events. This increase in seismic activity is noteworthy, given the area's reputation as one of the most earthquake-prone regions on Earth, where the Indian plate and the Eurasian plate collide. The seismic activity in this area is heavily influenced by various fault lines, including the newly active Almora fault. Significant seismic events in January, October, and November of 2023 have been linked to this fault, each followed by numerous aftershocks that contribute to an overall increase in seismic disturbances across northern India and Nepal. The soft soil of the Gangetic Plains, which extends across much of North India, intensifies the seismic energy from these earthquakes, increasing their impact, particularly in densely populated areas like Delhi National Capital Region. The discovery of helium-3 in the hot springs of Tibet by Simon Klemperer and his team from Stanford University introduces a new dimension to our understanding of geological processes. Helium-3 is a rare isotope typically found in the mantle, and its presence in surface springs suggests an unusually thin crust in the region. This finding indicates that the mantle is alarmingly close to the surface, hinting at significant tectonic movements beneath Tibet. Furthermore, the collision of the Indian plate with the Eurasian plate, which has been ongoing for millions of years, is crucial in understanding the increased earthquake rates in these regions. This tectonic collision has led to significant geological transformations, including the uplift of the Tibetan Plateau and the formation of the Himalayas. The process involves the subduction of the denser oceanic plate beneath the lighter continental plate, a phenomenon that triggers earthquakes and contributes to the formation of volcanic arcs. This complex interaction of tectonic plates not only shapes the physical landscape, but also poses significant risks. The recent pattern of earthquakes could indicate a buildup to more severe seismic activities. Local authorities and geological experts are therefore intensively monitoring these developments, updating seismic zoning maps, reinforcing building codes, and promoting public awareness to enhance preparedness for future seismic events. The findings from Tibet, where the dynamics of tectonic movements reveal the thin crust and the close proximity of the mantle, challenge previous geological models and provide new insights into the processes that shape our planet. These discoveries underscore the dynamic nature of Earth's geology, revealing intricate processes that could have broad implications for understanding mountain formation and seismic activities globally. In essence, the Earth beneath our feet is far from static. The ongoing and dynamic geological processes remind us of the planet's continuously changing nature, offering new puzzles and revelations with each discovery. As researchers like Simon Klemperer continue to explore these complexities, our understanding of Earth's geological past, present, and future continues to evolve, highlighting the incredible complexity and dynamism of the planet we call home. Next, discover the surprising geological activities unfolding beneath Bhutan's quiet terrain. Bhutan at the heart of plate collision drama. New and unexpected geological events are happening in Bhutan, showing signs that go against what scientists usually expect. In this quiet part of the world, extraordinary activities are occurring beneath our feet. Researchers believe that the mantle has reached and penetrated the crust, setting the stage for seismic phenomena that defy simple explanations. This anomaly gains significance when paired with regional earthquake data, which supports the theory that this mantle intrusion originated from the plateau's eastern flank. The unique configuration of the Indian plate, notably thicker in the north and considerably thinner on the sides, plays a crucial role in the geological dynamics of the area. This setup contributes to complex tectonic activities, leading to increased seismic events and significant geological transformations. The central area of the Indian plate shows a tendency to sink faster than its thicker northern parts, which aids the upward movement of mantle material. This movement helps in the recycling of the plate material, akin to the shedding of old layers. The ongoing subduction and collision between the Indian plate and the Eurasian plate, which started around 50 million years ago, are key to understanding these phenomena. As these plates collide, the Indian plate, with its variable thickness, undergoes different rates of subduction, resulting in notable geological consequences like the uplift of the Tibetan Plateau and the Himalayas. This process is similar to other known subduction zones where oceanic plates dive beneath continental plates, creating mountain ranges and volcanic activity. Moreover, the collision has thickened the continental crust under Tibet and the Himalayas, effectively doubling the crust's average thickness in these regions. This thickening process has profound impacts on seismic activity, contributing to the frequent earthquakes observed in the area today. Despite the significant uplift, the forces of erosion and weathering continue to shape the landscape at a similar rate. These tectonic activities and their implications are continuously studied, with recent seismic data providing more insights into the detailed interactions at play. These findings not only enhance our understanding of the region's geodynamics, but also have the potential to reshape aspects of Earth science related to plate tectonics and continental transformations. But here's where it becomes even more intriguing. The mechanisms behind these tectonic shifts are not just a curiosity, they are a clarion call for preparedness. The ground beneath us is not as steadfast as we once thought, and these newfound cracks and shifts are testimonies to the dynamic planet we inhabit. Yet, One might wonder, how did such a seismic secret come to light? Enter Stanford University's geophysicist, Simon Klemperer, a trailblazer in geological exploration. Simon focused on a unique area in northeastern India near Bhutan, known for its unusual geological activities due to tectonic plate movements. Equipped with cutting-edge technology and a robust passion for discovering new knowledge, Simon chose a particularly interesting method to probe what lies beneath the Earth's surface. His technique involved tracking various types of helium gas, especially the rare helium-3, which seeped up through the region's natural springs. Helium-3, a lighter and stable isotope of helium, has one neutron less than the more common helium-4. This distinction endows helium-3 with unique nuclear properties, making it a potential cleaner fuel for nuclear fusion reactions, as they produce less radioactive waste compared to traditional nuclear fission. One of the remarkable properties of helium-3 is its behavior at extremely low temperatures. When cooled to just a few thousandths of a degree above absolute zero, helium-3 transitions into a superfluid state, characterized by zero viscosity and the ability to flow without energy loss. This phenomenon highlights the unconventional superfluid nature of helium-3, quite distinct from helium-4 due to the quantum mechanical differences related to their nuclear spins. Despite its promising applications, helium-3 is incredibly scarce on Earth, found in only minute quantities. It is primarily sourced from the decay of tritium, a radioactive isotope, or from deep within the Earth's mantle. Interestingly, the Moon's surface has been identified as a potential rich source of helium-3, delivered there by billions of years of solar wind bombardment. This has sparked discussions about the feasibility of mining the Moon for helium-3 to meet Earth's future energy needs. However, harnessing helium-3 for energy on a commercial scale, especially through fusion, still faces significant scientific and engineering challenges. Current fusion reactors are not yet efficient with helium-3, requiring much higher temperatures for fusion reactions than those using other isotopes like deuterium and tritium. Moreover, while the Moon holds significant amounts of helium-3, the logistics and economics of lunar mining and returning it to Earth present formidable challenges that are yet to be overcome. In total, while helium-3 holds potential as a future energy source, significant advancements in fusion technology and space exploration are needed before this potential can be realized. To conduct his research, Simon collected water samples from over 200 springs across an area spanning almost 600 miles. His diligent efforts led to groundbreaking discoveries. He identified a clear boundary where deep Earth mantle rocks, known as crust rocks, came into contact without showing any signs of subduction, typically observed when one tectonic plate slides beneath another. This was not observed here, indicating a unique geological scenario. Further south of this boundary, Simon analyzed 3 specific springs. The findings from these springs were remarkable, showing clear signs of mantle characteristics. This suggested an incredible possibility. The Indian plate, one of Earth's large tectonic plates, was actually splitting apart. These discoveries have significant implications. They provide insights into the structural integrity of continents and the processes leading to earthquakes and other geological events. By identifying where the plates are splitting, scientists can better predict such events, potentially saving lives and minimizing damage from natural disasters. Simon Klemperer's work is crucial not only for the scientific community, but also for the local populations in these regions. Understanding the geological environment can aid in designing safer buildings and infrastructure. This mission was more than just about gathering data. It was about assembling a puzzle that dates back millions of years to the very origins of Earth itself. Simon Klemperer's relentless pursuit of knowledge underscores the importance of curiosity and dedication in science. His work is set to inspire future generations of scientists to explore the unknown, armed with the hope of making their own revolutionary discoveries. This groundbreaking revelation is not merely academic. Understanding the complex behavior of tectonic plates could revolutionize how we predict and prepare for earthquakes. It's akin to deciphering Earth's own playbook, offering strategies that might one day save countless lives, not just in the Himalayas, but across all earthquake-prone regions globally. By delving into Earth's subterranean mysteries, researchers like Simon Klemperer help us appreciate its dynamic nature. Their work reminds us that Earth is not a static entity, but a living, moving system whose secrets are continuously being revealed through the dedicated efforts of scientists around the world. Delve into how the seismic shifts of the Indian Plate might alter our global landscape. How the Indian Plate's fracturing shapes our Earth forever. In the complex realm of geological research, the recent indications that the Indian Plate might be splitting have underscored our limited understanding of the forces that operate beneath our feet. It's comparable to assembling a multi-dimensional puzzle where every discovery not only provides answers, but also opens the door to even more perplexing questions. This relentless pursuit of knowledge is not merely academic. It profoundly affects the very ground we walk on. And with each seismic revelation, our planet's narrative is continually rewritten. To grasp the complexities of Earth's inner workings, particularly in light of recent data about the Indian Plate, it's crucial to explore various geological phenomena and the implications of plate tectonics. Recent seismic investigations have shown that the Indian tectonic plate is bifurcating beneath the Tibetan Plateau. This process involves more than the subduction of the Indian Plate beneath the Eurasian Plate. It includes a complex interaction where parts of the Indian Plate are delaminating, its denser base sinking into the mantle, while its lighter top continues to scrape beneath the Eurasian Plate. This type of tectonic activity contributes to the dramatic topography of the Himalayas and could increase earthquake activity due to the stresses involved in this structural transformation. Volcanic activity is another critical aspect of tectonic movements. Volcanoes typically form along plate boundaries where subduction or the divergence of plates can create the conditions necessary for magma to ascend to the surface. Areas like the Pacific Ring of Fire are prone to frequent and often violent volcanic eruptions due to the subduction of oceanic plates beneath continental plates, which melts and recycles the crust to form new volcanic structures. Earthquakes are largely a product of tectonic stresses and occur primarily along plate boundaries where plates collide, slide past one another, or diverge. The movements along these boundaries can cause sudden releases of energy, resulting in the shaking of the Earth's surface. For instance, the San Andreas Fault in California, a transform boundary, is well known for its potential to generate significant earthquakes due to the horizontal sliding of the Pacific and North American plates. Understanding these dynamic processes is essential for predicting and mitigating the risks associated with natural disasters like earthquakes and volcanic eruptions. Furthermore, the ongoing study of plate tectonics reveals that Earth's lithosphere is far more intricate and dynamic than previously understood. The theories of continental drift and plate tectonics, which explain the movement of continents over geological time, have been foundational in understanding Earth's geological history and the formation of its landscapes. As research progresses, the findings from studying the Indian Plate's activities beneath the Himalayas and other tectonic regions worldwide underscore the complexity and dynamism of Earth's interior. This ongoing narrative of discovery and debate is not just for academics or adventurers, it's a crucial storyline in our understanding of how to coexist with and manage our planet's unpredictable nature. As the ground beneath us shifts, so too does our perception of stability and safety. The Earth has its own plans, and our theories and models are constantly catching up. Thus, as we grapple with these findings, the question is not only how the Indian Plate is splitting, but what new secrets will be unearthed in the process. This is not merely scientific exploration. It's a race to adapt our understanding and preparedness for what the Earth might present next. Examine the debates over the potential upheaval caused by the Indian Plate's dramatic transformations. The disconnection of the Indian Plate. The potential delamination of the Indian Plate is raising alarms throughout the region, pointing toward a turbulent future that might include everything from rampant landslides to significant climatic shifts. Yet, in a society captivated by over-the-top narratives, it's valid to question whether the dramatic portrayal of these geological transformations might be somewhat exaggerated. Indeed, the notion of the ground splitting beneath our feet provides a riveting narrative, but is the situation really as catastrophic as some might suggest? We are witnessing a significant geological drama beneath the Indian subcontinent. This isn't merely a trivial seismic disturbance. It's a profound tectonic transformation that could drastically reshape the landscape. Imagine enormous landslides set off by the shifting earth, potentially wiping out everything in their path and perhaps even causing rivers to forge new paths, creating brand new waterways. This scenario resembles a script for a natural disaster movie, complete with chaos and unforeseen developments. This geological activity has a substantial impact on climatic patterns, particularly affecting the monsoon systems vital to South Asia. The heat from the rising plateau intensifies monsoon circulation, altering the distribution of rainfall that is critical for agriculture in this area. Research indicates that the Tibetan Plateau serves as a significant barrier that alters atmospheric circulation, thereby influencing monsoon patterns throughout South Asia. As the plateau continues to rise, it could cause variations in monsoon behavior, potentially altering the timing and intensity of seasonal rains. Such changes might affect water availability for agriculture, jeopardizing food security and water resources across the region. Whether rainfall increases or decreases, the outcome could be flooding or drought conditions, both of which could disrupt ecosystems and agricultural communities. Furthermore, the role of the Tibetan Plateau in influencing monsoons extends beyond local effects. It helps regulate regional climate dynamics, which can alter precipitation patterns across a broader area, including Central Asia. The intricate interaction between the plateau's physical features and atmospheric dynamics contributes to considerable climatic variability across the continent. The contribution of the monsoon to moisture transport is essential for extreme precipitation events in the Tibetan Plateau region. This moisture transport is primarily driven by the South Asian monsoon, which plays a crucial role in replenishing water sources in the region during the summer. The impact extends beyond just human communities. Wildlife and entire ecosystems might find themselves challenged by the evolving environment. Species accustomed to current altitudes and climates could struggle to survive as their habitats undergo transformations. This could lead to shifts in biodiversity, with some species potentially vanishing. It's a vivid reminder of how interconnected our planet's systems are, and how subsurface changes can lead to significant challenges for those living above. As the Tibetan Plateau rises due to tectonic activities, not only is the physical geography reshaped, but the socio-economic landscape across South Asia also faces significant challenges. This region, heavily reliant on monsoon patterns influenced by geological changes, confronts profound issues. The monsoon systems vital for South Asian agriculture are affected by the heat emanating from the plateau, which can shift rainfall patterns and disrupt the availability of water needed for agriculture and drinking purposes. Frequent earthquakes and landslides pose a significant risk to infrastructure, including roads, bridges, and buildings, particularly in regions like the Western Ghats in India, where landslides are a common monsoon calamity triggered by intense rainfall. These natural disasters not only cause immediate disruption, but also result in long-term economic impacts due to the extensive damage to property and infrastructure, loss of lives, and the considerable expenses associated with rebuilding and mitigation efforts. In areas like the Western Ghats, there has been a consistent pattern of landslides each monsoon season since 2018, causing substantial losses in terms of both lives and economic stability. Similarly, research from places like Aranayake, Sri Lanka, highlights the direct impacts of landslides on local socio-economic systems, providing detailed assessments of the affected areas and quantifying the economic losses incurred. Utilizing socioeconomic data combined with geographic information systems is vital for accurately assessing the impact of these disasters. This integrated approach aids in gauging the extent of damage and facilitates effective planning for mitigation and reconstruction. Comprehensive landslide inventories, such as those compiled by the Indian Space Research Organization, are crucial for enhancing planning processes and reducing future risks. Historical incidents like the 2017 earthquake in Mexico and the 1939 Chilean earthquake in Chile are stark reminders of the dramatic and often devastating impacts of tectonic activities. The 2017 earthquake, particularly in Puebla, showcased the destructive power of tectonic forces when a segment of the tectonic plate unexpectedly split, leading to significant casualties and widespread infrastructure collapse across multiple states, including Morelos and Mexico City. This event was particularly impactful because it occurred shortly after a national earthquake drill, catching the populace off guard. The 1939 Chilean earthquake in Chile was even more catastrophic, resulting in at least 28,000 deaths and becoming one of the deadliest earthquakes in the country's history. The immediate destruction was followed by long-term socioeconomic impacts, prompting the Chilean government to initiate major infrastructural and industrial reforms through the establishment of the Production Development Corporation. These historical examples underline the essential need for robust infrastructure capable of withstanding geological disturbances and for comprehensive disaster preparedness and response strategies. The stability of regions prone to seismic activity, such as India and its neighbors, is intricately linked to the movements of the tectonic plates beneath them. To effectively prepare for such events, it is crucial to understand the full scope of risks and potential changes. Enhanced seismic monitoring systems could provide early warnings, potentially saving lives and reducing damage. Strengthening infrastructure to better withstand earthquakes and educating the public on disaster preparedness are also critical measures. Additionally, advanced research into the behavior of tectonic plates could lead to new methods for predicting and mitigating the impacts of these deep earth processes, further safeguarding vulnerable regions from the worst of nature's fury. Incorporating geological risk assessments into urban planning and environmental policies is crucial for protecting future developments from significant natural events. This process requires incorporating disaster risk reduction (DRR) strategies into development planning and legal frameworks at various levels, national, regional, and local. A methodical approach is used to assess risks, pinpoint essential DRR measures, and integrate these measures into development activities guided by strategic policy documents that dictate planning, budget allocations, and public investments. Legal and regulatory frameworks support these strategies by setting up institutional mandates and systems of accountability that prioritize risk reduction. These frameworks might include specific disaster management laws or the inclusion of risk management in sectoral laws that impact critical economic sectors like agriculture, manufacturing, and tourism. These sectors often play a significant role in generating development-related risks. Financial strategies are also pivotal in aiding recovery efforts after disasters. These strategies encompass insurance schemes and relief funds that provide necessary financial support to assist communities in rebuilding and recovering. Effective financial protection mechanisms are vital for sustaining economic stability and facilitating a swift response and recovery after disasters. Moreover, international standards such as those from the International Organization for Standardization regarding environmental management systems and risk management offer guidelines that aid cities and communities in boosting their resilience. These standards, typically developed in response to demands from industries or consumer groups, ensure a high degree of ownership and compliance, thus easing the integration of risk management into urban planning and development. Integrating climate change adaptation into disaster risk reduction in urban environments is equally essential. This integration aids in reducing vulnerabilities in cities, which are frequently most affected by the impacts of climate change. By incorporating CCA into urban planning, cities can undertake coordinated and strategic actions to manage risks effectively, thereby increasing their resilience against climate-related and other geophysical disturbances. Advancements in technology, particularly in monitoring and predictive modeling, could revolutionize how we respond to geological threats. Embracing cutting-edge innovations allows us to preempt nature's surprises, using human ingenuity to foresee and mitigate the Earth's more destructive actions. Ultimately, while the delamination of the Indian plate poses a significant challenge, it also forces us to reconsider our relationship with the planet. This situation calls for respect and responsiveness to the powerful natural forces that mold our environment, reminding us that we are essentially navigating the complex and sometimes hazardous terrain Earth provides. Could the dramatic geological changes be even more catastrophic than predicted? How prepared are we? Like, comment, and subscribe to discuss more on these unpredictable tectonic shifts.